A warm welcome. This is Control Systems course lecture 3.2 focusing on Bode plot. Generally, the frequency response can be represented in certain different types of plots which are different from the ordinary graphical representations. The plots normally used are the Bode plot, polar plot. The polar plot is otherwise called Nyquist plot. In Bode plot, a semilog sheet is used. That's a semilog graph sheet is used, which consists of two y-axis and one x-axis. The two y-axis are used to represent the magnitude and the phase angle of the sinusoidal transfer function, and the x-axis will represent the angular frequency omega value in the graph sheet. Now we can draw two plots in the same graph. One is the magnitude of the sinusoidal transfer function versus the logarithmic omega, and the other one is the phase angle of sinusoidal transfer function versus the logarithm of omega value. The main advantage of a Bode plot is that multiplication of magnitudes can be converted into addition. Actually, this is a very simple method of sketching an approximate log magnitude curve. The Bode plot is a frequency response plot of the sinusoidal transfer function of a system, and it is a plot of the transfer function magnitude and phase angle as a function of frequency. The gain magnitude many times is expressed in terms of decibels. That is, we will not consider the gain as, for example, say capital G, we will not consider in terms of A while drawing in the Bode plot. We used to consider that as 20 logarithm to the base of 10 of A. That is, in terms of decibels we will be considering. So what are all the basic factors of the transfer function? They are: first point, it may be a constant gain. Second, it may be an integral or derivative factors. That is, if it is an integral factor, it is 1 by j omega, and if it is a derivative factor, it is j omega. Or else it may be a first order factor. That is, it may be 1 plus j omega t, or else 1 by 1 plus j omega t, or else it can be a quadratic factor which is consisting of 1 plus 2 zeta into j of omega by omega n plus j omega by omega n the whole square, or its reciprocal. So these are the basic factors of g of j omega normally. And this is how the semilog sheet will be focused. This is the semilog sheet representation. So the graph which is present in the top is known as the magnitude curve, and this is the phase curve. So magnitude curve is also drawn. Here we have taken the magnitude values are from 40 to minus 60, and we have drawn the graph here. Normally this magnitude graph is drawn with the scale, along with whether it is a pencil or pen what we use. So scale will be used for drawing the magnitude curve, and while considering the phase curve, here we can see that the angle is from 90 degrees to minus 270 degrees, and here it is a free line diagram. With the free hand we have to draw this curve. We have to take a number of points according to the frequency, and then we can connect to form a very good phase plot. In this way, both the magnitude as well as the phase plots can be represented with respect to the same frequencies. Here at the bottom, it is the frequency has been represented as, here it is 10 power minus 1, that is 0.1, and here it is 0.1, the next point is 0.2, this is 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and it is 1 here, that is 10 power 0. Here it is 1, and the next point is not 1.1, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, here it is 10, that is 10 power 1. And after 10, you have to consider this as 20, 30, 40, 50, 60, 70, 80, 90, 100. That is 10 power 2. So in this way, the frequency has has to be considered in decades. We call this pattern from here to here, it is a decade. So one decade will be consisting of a similar scale. If you are taking 0.1 in this decade, that's a 0.1 scale. If you are taking 1 in this decade, it is a 1 scale. If you are taking 10 in this scale, in this decade, then it is a 10 scale. This is how the frequency is represented in radian per second. If k is greater than 1, it will be having this much value. If k is equal to 1, this is the value. If k is less than, or if it is less than 0, less than 1, and between 0 to 1, here it will be represented. It's a constant term. And next is the angle phi, it is 0 degree. So the angle is at 0. This is what is a constant. While considering the integral factor, g of s is equal to k divided by s. So g of j omega is equal to k by j omega, which can be represented as the magnitude value is k by omega, angle is, since j omega term is present in the denominator, we have to represent that as minus. Omega value alone, that is j omega, means it has to be indicated as 90 degrees. Because even if we take the tan inverse value, we will get minus 90 degree. That's a tan inverse of imaginary part to the real part. If we consider the real part is 0 here, it's not the value here, only imaginary part is present in here. This is j omega alone. So tan inverse of imaginary part is omega divided by real part is 0. So automatically tan inverse of infinity. In tan inverse of infinity is nothing but 90 degrees, and since it is present in the denominator, we will be putting it as minus 90. So we can see the gain value is 20 log of k by omega, and phi is minus 90 degrees. Since it is a minus 90 degree one, we can see here it is minus 90 degree, the constant value, and the graph, it is 20 log of k by omega. As omega increases, the slope is a decreasing one. This is integral factor. If we consider a derivative factor, it is ks, so k omega, since it is present in the numerator itself, we have 90 degrees. So gain angle, this is an increasing one, and it is plus 90 degrees. Next, let us consider the first order factor. While considering the first order factor in the denominator, so g of s is equal to 1 by 1 plus st. So we have 1 plus j omega t. We know the magnitude is root of 1 square plus j, here j square is, we are not going to consider that, x plus jy is root of x square plus y square. So root of 1 square plus omega square t square. The angle is, since it is present in the denominator, it is minus tan inverse of imaginary part to real part. Real part is 1, so imaginary part is omega t. So tan inverse of omega t. So this is the one, we have magnitude and angle. If we see the graph in this case, we can see that there is a constant term as well as there is an integral term divided by omega. So what will happen is, here we will have a constant term, and then here we will have an integral term. It is decreasing. Similarly, while you see the angle, this angle will be less than 0 degrees because it is minus here. So is less than 0 degrees. Between 0 and minus 90 degree, the value will be there. While you are considering the first order factor in the numerator, then we will have a value of root of x square plus y square. So root of 1 square plus omega square into t square. Angle is tan inverse of omega t. So here it will be a constant term representation and then a derivative term. It is an increasing one. And by looking at the angle, it's between 0 degree and plus 90 degrees. Quadratic factor in the denominator positive. So if we see the values here, this is how, this is actually an increasing part. When the zeta value is very less, we can see the oscillation is heavy in the negative direction, and after that it is increasing. When the zeta value is getting increased, the oscillation is suppressing itself, and when it is when the critical damping is applied, we can see that the curve starts from 0 and then starts increasingly. And similarly, we can see the angle also. The angle as such, when it increases, when zeta is getting increased, at critical damping, the value is almost a linear and it's not a parabolic curve or exponential curve, etc. Thank you. And this is how the magnitude or Bode plot is calculated for drawing the graphs. The first step is you have to convert the transfer function into Bode form. That is, we have to substitute the value of s is equal to j omega, and then we have to frame the magnitude as well as the angle part. Next, let us draw this table. Here we have a term, the corner frequency, the slope, and the change in slope. Corner frequency term is nothing but the frequencies which are present in the system itself. Actually, we have already discussed about 5 factors. A constant factor which will not have any frequency. Next is the derivative factor and the integral factor. The integral factor will be consisting of 1 by j omega term, and the derivative factor will be consisting of j omega term. Similarly, we have first order factor and then the second order factors. Depending upon that, I mean, we have to find out the corner frequency values for each term, and while writing in this table, we have to write it in an order, that is the increasing order of the frequency value. And next, we have to arbitrarily choose two values of frequencies. One is the lowest frequency and one is the highest frequency. That is, while considering the corner frequencies of the system, for example, suppose if we are having 4 corner frequencies, then we have to choose the lowest frequency which is less than the corner frequencies present in the table, and also we have to choose a higher frequency which is greater than the higher value of the corner frequency present in this table. So we'll have a limit, and then we have to calculate the gain value. What is the change in gain from omega x to omega I? That is from one frequency to another, because we have corner frequencies. Only at the corner frequencies we are going to calculate the gain value. So we'll get a gain value as such. And next is what we have to do is we have to take a semi-log sheet. Then we have to draw the required range of frequencies as well as the dB value, because we have calculated the gain in dB here, and so the gain values can be represented in the left hand side of the y-axis. That, and then we can draw it down. And next, what you have to do is you have to calculate the phase plot. Phase plot representation is very simple. For varying values of omega, including the corner frequencies, just we have to substitute the omega value in the phase of the transfer function. We have already we would have already formed the phase of the transfer functions. Transfer function exactly, or each term will be separated differently with the phase values, as we have already seen for all the factors. And the omega value is then get substituted. And among the omega value, all the corner frequencies have to be selected. In such a way, we'll be getting an increasing or decreasing value of phase values. It can be marked in the phase, another y-axis have to be taken in the graph. On the right hand side, you can mark it, or in the graph sheet itself, top layer can be used for the magnitude value, and the bottom layer can be used for the phase value, whatever it is, that's up to our choice. And then we have to draw the y-axis, second y-axis for the phase angles, because we have calculated the phase angle now. The total phase angle for the given transfer function, and this can be taken as a y-axis with respect to the same omega values which we have tabulated. We can mark all the points, and by joining those points, we'll get a smooth curve. This is how the phase plot of the Bode plot is drawn. This is how we'll be getting the magnitude plot. As I have already told, the magnitude plot will be represented with the help of scale and pencil. So it is almost straight lines, whether it is decreasing or increasing or straight line, will be getting it's a straight lines representations, and while considering the phase plot, it's a curve. Now let us find out the gain margin and the phase margin. First, let us start with the gain margin. So while considering the gain margin, the term is, what we have to consider is gain. At gain margin, the frequency is phase crossover frequency. So what we have to do is we have to take 180-degree phase angle, whether it is 180 or minus 180. So 180-degree phase angle, you have to draw a line, or you have to consider this 180-degree angle and look into the point where it cuts the phase plot. That frequency is known as phase crossover frequency omega pc. And next you can mark this as phase crossover frequency, and at this point look into the gain value what we have achieved. You just take a look of the value in decibel for the gain margin. Along with this, you can, this is the value of the gain margin directly obtained. You can also consider the negative value of the gain margin so that it will be the perfect one. And next, while you are considering the phase margin calculation, we have to consider zero value here. By definition, it has to be considered unity in the transfer function or zero in case of logarithmic representation. That is, when it is represented in decibels, you have to consider it as zero. So you take 0 decibel value, you consider the point where this 0 decibel cuts the magnitude plot, and you bring it down, find out the gain crossover frequency at that point. And at this gain crossover frequency, you can see it cuts the phase plot. So this value can be found out for the respective phases, and this is called phi GC. What we used to do with the phi GC? Phase margin formula is phase margin is equal to 180 degree plus phi GC. So you just find out phase margin is equal to 180 degree plus this phi GC value. Whatever angle you are getting, that will be the phase margin value. This is how the phase margin and gain margin are plotted in the Bode plot. Thank you.